Welcome to the Copper Spice YouTube channel, and thanks for joining us. In this video, we are going to talk about the ideas of thread-safe code as it relates to a multi-threading application. Thread safety. Our discussion will start by accurately defining the terms associated with thread safety. This talk is going to focus on the different levels of thread safety, when it is a concern, is conditionally thread-safe code enough, and how reentrant code differs from thread-safe code.
The concept of thread safety relates to asking, can a section of code be called from multiple threads simultaneously and not violate certain threading constraints? In order for a function to be thread safe, it must work correctly even under these conditions. This means all resources must be protected so that no undefined behavior occurs. For example, writing to the same variable from two different threads at the same time needs to work correctly. Avoiding a crash, undefined behavior, or a deadlock is not enough. The code must actually produce the correct result, which is a requirement that can be easy to overlook. If you can get away with code which is thread unkind or thread hostile, by all means consider doing so. If your program is single-threaded, the question of thread safety is not a huge concern. There is nothing inappropriate with writing unsafe code in respect to threading, as long as it is never invoked from more than one thread at the same time. Of course, you should not write code which has undefined behavior or is invalid, but thread-safe code is not always required. Writing thread-safe code can be more complex, and often there is extra work required at runtime to ensure thread safety is observed. Even in a multi-threaded application, not every function or method needs to be thread-safe.
This is a theoretical example to demonstrate the abstraction for a thread-safe function. So let's start with a method called makePie, where a chef is passed a type of fruit and he makes the appropriate pie. If this method existed in a single-threaded application, then the chef would take one order, make the requested pie, and hand it over to the customer. There would be no opportunity to have multiple orders and no risk of mixing up the pie orders. This would be slow, inefficient, and not a great way to run a pie business. In a multi-threaded application, multiple customers will be able to order pies at the same time. The idea of two customers, each ordering a pie, can be thought of as calls from different threads to the same function. Since we said the makePie method is thread-safe, there is a guarantee that these simultaneous requests will work in a multi-threading environment. The chef does not need additional instructions from the calling thread, such as stop making pie A and start making pie B, how to share the oven, or when to sharpen his knife. All of this is up to the chef class and part of the makePie method. In terms of threading, there is actually no way for the caller to indicate or control what order a pie will be produced. These are the fundamental principles of a multi-threaded application.
Based on our chef example, it is fairly easy to figure out what resources will be needed and where there might be conflicts. When the customer orders the pie, there is no need to ask the chef if he knows how to share the oven resource. So describing what it takes for code to be thread-safe is not all that complicated. Avoid race conditions. If there is shared data, ensure some kind of barrier is in place. Use an atomic operation, or consider redesigning the code. If there is no shared or mutable data, then the code is very likely to be thread-safe automatically. The complexity is how to implement a thread-safe function when there is shared data. The makePie method was designed to be thread-safe, so it must contain some mechanism to protect the oven. The code in the method needs to ensure that while a pie is baking, no one changes the temperature of the oven or tries to add a second pie. Additional code might be required for the chef, since he might be working on multiple pies at once. The method may need to consider how to keep the fruit organized so the pie fillings are not mixed up. Understanding what makes a function thread-safe is the easy part, and usually not complicated to define. The trade-offs and challenges occur in how to efficiently implement a thread-safe function. Thread safety can be broken down into three major levels. One end of the thread safety spectrum is code which is thread safe. The other end is code which is thread unsafe, unkind, or hostile, and cannot be called for multiple threads. In between these two types of code is an intermediate level called conditionally thread safe. This middle level is where a majority of code resides, especially when the function is not dealing with any shared resources or global data.
The trade-offs which may be necessary to implement thread-safe code is a very large topic. Our intent in this presentation is to explain when you should be concerned and how much thread safety is required. The fundamental idea behind implementing thread safety is either eliminating or carefully managing shared state. Whenever shared state can be avoided by using immutable data, thread local storage, or some other mechanism, your code will be thread safe by default. If shared state is required, the data must be protected either by using an atomic data type or serializing the access, so only one operation can occur at a time. The libguarded library was developed to manage access to shared data at a higher level of abstraction. For more information on this library, we encourage you to watch our existing presentation on the libguarded library.
The concept of conditionally thread safe is a middle ground between fully thread safe and completely unsafe. A conditionally thread safe function is thread safe as long as two threads do not operate on the same object at the same time. This is a common occurrence, and a majority of C++ methods are in fact conditionally thread safe. For example, the method pushback in std_vector operates on a particular vector. Calling this method from different threads at the same time is considered safe, as long as the threads are operating on different vectors. If multiple threads try to modify the same vector, then the condition for conditionally thread safe is no longer satisfied. The pushback method is now not guaranteed to be thread safe. For code that is conditionally thread safe, there is a requirement for the threads to access different objects to ensure there is no possibility of a threading problem. Let's look at another method in our chef class. MakeCake is conditionally thread safe. What does this mean? Given the preceding definition, there can be any number of chefs making any number of cakes. However, a given chef must be focused on their unique cake. Multiple chefs cannot work on the same cake, nor can a given chef work on two cakes. This would not adhere to the constraints of conditionally thread-safe code. In this example, the oven is still a shared resource, so managing access must be protected. In an ideal kitchen, it would be an advantage to have numerous ovens, so no one needs to share. This is where some of the trade-offs occur. How many ovens are practical, and what does it cost to have more ovens when you only need the extra ones occasionally?
Reentrant code, or a reentrant function, is often inaccurately associated with multithreading. We looked around on the internet and found a few definitions for a reentrant function. The first two appear to conflict with each other, and the second one is really the definition for conditionally thread safe. The third one is incomplete, and the last one is rather vague. When talking about thread safety, many developers use the term reentrant code incorrectly. We need an accurate definition based on computer science. The idea of reentrant code came about long before multitasking operating systems existed. Although there are conflicting definitions on the internet, there is a computer science definition which we believe C++ adheres to. The purpose of a reentrant function is to allow the function to be interrupted and then called again before the first call completes. This interruption might be a hardware interrupt or a signal such as a seg fault, an exception, or some other mechanism that transfers control without the function completing. The idea of reentrant code actually has nothing to do with threads and is only concerned with what happens when the function is interrupted. A reentrant function could be called from multiple threads, but only if it is also thread safe.
Using the idea of our prior example, MakePie is now reentrant but not thread safe. Customer A can order a pie, and then she can interrupt the chef to add another pie to the original order. Since this code is reentrant, the chef is perfectly able to stop what he is doing, make a different pie, and then resume work on the first pie. The problem happens when customer B tells the chef to work on a completely different pie. Since this customer is equivalent to a different thread, and the code is not thread safe, the chef gets confused. There is no telling what pie will be made now. It is just as likely the chef will make an apple boysenberry pie or a pie with no fruit. This method could be designed to be thread safe, but it would have no relation to the fact that it is reentrant. Code can be reentrant or thread safe, and there is actually no connection between these two concepts. A function which is reentrant can be thread safe or not thread safe, just like any other function. The idea that it is reentrant has nothing to do with how the function behaves in a multi-threaded environment. Multi-threading has to do with two or more operations occurring simultaneously, whereas reentrancy has to do with one operation being interrupted and therefore stopped while another operation occurs. For use in a multi-threaded application, it is very important to document which functions are thread safe or conditionally thread safe. Having code which is reentrant may not be required all the time, but if you have functions which do need to be reentrant, this should be documented and not merged with thread safety. We believe it is very important to use consistent terminology and concepts that conform with computer science and the C++ standard. Terms should be fully specified so you are not assuming everyone means the same thing when they say thread safety.
Here is an interesting example of what can occur when definitions are not carefully considered. The Qt framework decided to use the term reentrant for what is actually conditionally thread safe. Their definition for reentrancy does not address the conflict with the existing computer science terms. There is also no mention of conditionally thread safe in their documentation. We understand some developers say the terminology for multi-threading is not standardized, but there are standards. The problem happens when various companies and random people on the internet try to use their own definitions and end up confusing everyone. In our CopperSpice documentation, we use the term conditionally thread safe and not reentrant because these classes do not meet the traditional definition of reentrancy. As an example, the Q shared pointer class is actually conditionally thread safe, which means two different shared pointers can be altered by different threads at the same time. This is necessary to use this class in a multi-threaded program. When the Qt framework says this class is reentrant, they are not addressing the question of thread safety. Consider this example. A new value is assigned to a Q shared pointer, and this causes the old object to be destroyed. What if in the destructor of the referenced object some assignment happened? This would call the Q shared pointer operator equal method. However, since this destructor was called from the operator equal method, Q shared pointer would have to be reentrant for this to work. So do they mean this example works correctly, or have they mixed up the idea of reentrant code and conditionally thread safe?
Understanding the proper computer science definitions of these terms is important, since it will help you determine when some other developer is using these terms in a confusing or inaccurate way. A serious problem arises when a library developer says a particular class or method is reentrant, and then indicates this has something to do with thread safety. If someone is unaware of the difference between thread-safe, conditionally thread-safe, and reentrant, then you need to be careful using their code. It may be necessary to study the internals to see if what they say agrees with what they documented. The overall ideas of thread safety are not difficult or complicated to describe. The real issue is asking if the libraries and internal code in your application meet your required level of thread safety. Proving correctness in thread safety and dealing with the trade-offs is where multi-threaded programming starts to get fun. For more information about CopperSpice and libguarded, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.